So this is how you will find Lebesgue outer measure. This is a subset of R. So for this I am finding the all possible subcovers. For the covers we will find out the length of the interval, that is this will be an open bounded interval, this is open bounded interval. For this open bounded interval we are finding the length of an interval. So length of an interval will be a number. Similarly for this subcover I have found that N2 is the length of an interval. For IK3, N3 will be the length of an interval. So N1, N2, N3 will be the numbers. N1, N2, N3 or numbers. So out of these N1, N2, N3 so on, you will select the smallest. That is, you will find the infimum of all these numbers. Infimum of all these numbers. Okay, that is nothing but m star of A. So mathematically I can write m star of A is infimum of length, sum of length of an interval such that A is subset of union k is equal to 1 to infinity ik, and ik is open and bounded interval. Bounded interval. This is nothing but Lebesgue outer measurable set. So now m star has some properties. So first property is m star of phi is 0. So from definition of m star, I can write m star of A is equal to infimum of k is equal to summation of k is equal to 1 to infinity length of ik, where A is a subset of union of k is equal to 1 to infinity ik, in which ik is open and bounded interval. So we know that every open and bounded interval is a cover of phi. Okay, so I can write phi is a subset of A comma A for all A belongs to R. So if I find the length of this interval, it will be 0. So I can write m star of phi is less than or equal to 0. Since m star of phi is not less than 0, that means m star does not take negative value. M star of phi will be equal to 0. So first property holds good. So the next property is if A is subset of B, then m star of A is less than or equal to m star of B. That is nothing but whenever A is contained in B, then quantity of A is less than or equal to quantity of B. So pictorially I can write this is my A and this is B. Okay, so that is nothing but m star of A, this is m star of B. If whenever A is contained in B, then m star of A, that is quantity of A, is less than or equal to quantity of B. So B is subset of union, that is whenever B is subset of union I is equal to 1 to infinity II, then A is subset of union I is equal to 1 to infinity II. This is because A is subset of B. So therefore I can write every cover of B is also a cover of A. Correct? So this implies set of covers of B is subset of set of covers of A. So using M star definition, I can write summation I is equal to 1 to infinity L of ji such that B is subset of union I is equal to 1 to infinity L of ji will be less than or equal to, that is subset of summation I is equal to 1 to infinity L of I such that A is subset of union I is equal to 1 to infinity I. Okay, so here Ji is the open and bounded intervals of B and II is the open and bounded interval of A. So from the definition of Lebesgue outer measure, this is nothing but M star of B, which is less than or equal to, this is the definition of M star of A. Okay, sorry. So next you have to find infimum of all this set and infimum of all this set, that is infimum for set of covers of B and infimum for set of covers of A. So we know that if A is subset of B, then infimum of A will be greater than or equal to infimum of B. Here set of covers of B is subset of set of covers of A. So if I take infimum for this, infimum of B will be obviously greater than infimum of A. That is M star of B is greater than or equal to M star of A. In other words, M star of A is less than or equal to M star of B. You should note this point. If A is subset of B, then infimum of A is always greater than or equal to infimum of B. So how can I explain this? Infimum of A is greater than or equal to infimum of B whenever A is subset of B. Let us consider one example. I have a set 1, 2, 3. So infimum for this set is 1, isn't it? So I will retain this set as it is and I will include some more numbers, -1, 3, 2, etc. So if I find infimum for this set, infimum will be -1. So if I include more numbers, there are chances of infimum will be less, because there can be elements which have added extra which are lesser than the infimum what we have computed from the set which we considered first. So if you make your set bigger, then the infimum will be decreasing. So infimum of A is greater than or equal to infimum of B. I hope this concept is clear for all of you. The next property is countable set has outer measure 0, that is M star of C is equal to 0. In order to prove this, let us understand the definition of countable set. Countable set. So we know that if the set is finite, then we can count it very easily. In the case of infinite set, countability can be defined as it is a mapping from C to set of natural numbers. Since set of natural number is countable, if there exists 1, 1 and onto map between your set and natural number, then you will call that set as countable set. So now let us prove this property. So let C be the countable set. So C is equal to C1, C2, so on. I can write this set as Ck, k is equal to 1 to infinity. This is one of the possible subcover. One of the possible subcover for C. Subcover, okay. So we need to find all possible subcovers. Okay, we need to find all possible subcovers of C, which is not possible. Till infinity we have to find, so which is not possible. So consider you have C1, C2, C3, C4, C5, C6 and so on. So I am looking for cover of these set. Okay. So you can say that take the small intervals around these sets. Small intervals around these sets. Okay. So and take all those intervals and that will form one of the cover. You will consider what you will do. You will take the small intervals around these sets. Okay. And you will form one of the cover. But we have to take all such covers. For all the set we have to find the covers. So start with positive. Start with any positive number. Any positive number. So let us take epsilon. Given epsilon greater than 0. I am taking length of an interval around C1 as epsilon by 2. So how can I take this? C1 minus epsilon by 2 square comma C1 plus epsilon by 2 square. If I find the length of this interval, it will be epsilon by 2. This minus this, isn't it? C1 gets cancelled. Epsilon by 2 square plus epsilon by 2 square gives epsilon by 2. Similarly, for this epsilon by 2 square, that is C2 minus epsilon by 2 cube comma C2 plus epsilon by 2 cube, that is nothing but epsilon by 2 square. Similarly, around CK, I can take IK is equal to CK minus epsilon by 2 power K plus 1 CK plus epsilon by 2 power K plus 1. Okay. For all K belongs to natural numbers. So now IKs are open and bounded intervals. So I can write C is subset of union K is equal to 1 to infinity IK. So IK where K is equal to 1 to infinity is one of the cover of C. Okay. So C is subset of union K is equal to 1 to infinity IK. Here IK where K varies from 1 to infinity is one of the covers of C. So I can write infimum of summation K is equal to 1 to infinity L of IK such that C is subset of union IK will be less than or equal to summation K is equal to 1 to infinity L of IK. Why? Because this is M star of C, that is this is for all possible subcovers and this is for one of the cover. Correct? So one of the cover denirutte that will be greater than infimum of all possible covers. So M star of C is less than or equal to summation K is equal to 1 to infinity length of IK. So since I know what is IK, IK is nothing but CK minus epsilon by 2 power K plus 1 comma CK plus epsilon by 2 power K plus 1. I can find length of IK. So length of IK will be epsilon by 2 power K. Correct? So m star of C is less than or equal to summation k is equal to 1 to infinity epsilon by 2 power k. That is nothing but epsilon into 1 by 2 plus 1 by 2 square plus so on. This is a convergent sequence, that is nothing but geometrical progression. So this will be equal to epsilon half by 1 minus 1 by 2. That is, in geometrical progression, how we will find the value? A by 1 minus r. A is the first term 1 by 2. 1 minus r is difference between first and the next term, that is 1 by 2. So if I solve this, I will get epsilon. Therefore, m star of C is less than or equal to epsilon. Since epsilon is arbitrary, that is given thing, epsilon is greater than 0, m star of C will be less than or equal to 0. Since m star cannot be negative, m star of C will be equal to 0. So these are some of the properties of Lebesgue outer measurable sets. So now in the next session I will discuss 3 properties which m star should be satisfied. First one is m star of A plus y is equal to m star of A, and m star of union I is equal to 1 to infinity ei is less than or equal to summation I is equal to 1 to infinity m star of ei, and the last one is m star of I is equal to L of I. Okay. So the first property is m star of A plus y is equal to m star of A, that is nothing but translation invariance. So first let us define what is A plus y. A plus y is nothing but A plus y such that A belongs to A. Okay. So if this is a cover of A, covers of A, okay, covers of A, I will consider this as cover of A plus y. This is A and these all are covers of A. This is A plus y and these all are covers of, all possible covers of A plus y. So in order to prove this property, we have to note that if ik where k is equal to 1 to infinity is a cover of A, then obviously ik plus y is a cover of A plus y. Okay, this is first point. And the second point is if ik is open and bounded interval, then ik plus y is also open and bounded intervals. One more point is L of ik is equal to L of ik plus y. Okay, using these 3 points we will prove this property. So let's start with the definition of Lebesgue outer measurable set. M star of A is equal to infimum of summation L of ik such that A is subset of union of ik where ik is open and bounded interval. This is the definition of Lebesgue outer measurable set. So using one of the point here, I can write infimum of, so this is a ik where k is equal to 1 to infinity is a cover of A, then obviously ik plus y is also a cover of A plus y. And ik is open bounded interval, then obviously ik plus y is also open and bounded interval. So I can write length of ik plus y such that A plus y is subset of union ik plus y, and ik plus y is open and bounded interval, isn't it? So this is m star of A, and this will be a definition of m star of A plus y. So we have proved the property. What I have done is I have considered the definition of Lebesgue outer measurable set, that is infimum of summation length of ik such that A is subset of union ik, where ik is open and bounded interval. Since if ik is a cover of A, then ik plus y is also a cover of A plus y. I can write infimum of all summation length of ik plus y. Then A plus y is a subset of union ik plus y, such that ik plus y is a open and bounded interval. So this is like if and only if condition. Okay. So using this I have written this. This is nothing but definition of m star of A plus y. So m star of A is equal to m star of A plus y.